It's nice to be here. I was really, really hoping to actually be in Rangeley or in Quill Hill this evening with all of you folks. The forecast didn't look so good. It actually cleared off where I am in Waterville, but Sarah assures me there are still a few clouds up in the Rangeley area, which would have made it a little challenging with the telescopes. But hopefully next month we'll be there. I know we've been saying that a lot, but sooner or later it's going to hit us right. So we're going to do a virtual sky tour tonight. Let me bring it up here, and I'm going to adjust my screen just a little bit. And we're going to do things, if you've watched a few of these before, you know, I often start with the sun up, and tonight we've talked about the sun in the past. So I've set the thing so the sun's just below the horizon now. This is around 9 o'clock tonight, what it would be like if it were clear. And when we're out there, one thing we often do is we start looking at the sky, looking for the first star to come out. Have you ever laid there and watched the sky, waiting to see which stars come out? Well, obviously, the ones that are going to come out first are going to be the brightest ones. So I'm going to just let it slowly here for a couple moments, get a little darker, and just watch to see if you can see a star popping out of view, because you don't see anything, you don't see anything, you don't see anything, and then suddenly a star appears. And it shouldn't be too much longer. We'll start to see a star or two here. And it's always kind of magical, because once you see one, then suddenly someone sees another one, and then another one, and then they just start appearing in the sky. I see the first star. If you haven't seen it yet, it's right over here. And that star, I'm going to stop right there. We just got a whole bunch of stars popped out. I had gone a little faster than real time, so they wouldn't really pop out quite as fast as they did here this evening. But this will be the first star you'll see. It'll be in the southwestern sky tonight, and that is the star Arcturus. Arcturus is the fourth brightest star in the entire sky, year-round, not counting the sun, for nighttime stars. And the second brightest you can see from Maine, the brightest star being Sirius, which we see in the wintertime. The other two, Canopus and Rigel Kent, are never visible from Maine. They're in the southern hemisphere. So of all the stars we can see from the state of Maine, other than the sun, nighttime stars, Arcturus is the second brightest, and the brightest one you'll see outside tonight. But once you see Arcturus, you'll notice off to the east of it, you're going to see another bright star coming up. That's Vega, and Vega is the fifth brightest star in the sky. So you've got two of the brightest stars visible that will pop out first. And Arcturus, here it looks white, but you'll notice if you're outdoors and you look for it some night soon, it'll have a slightly orangish color. It is an orange star, which means it's a little cooler than our sun, a yellow star, but hotter than our red star, like Betelgeuse in the wintertime or Antares in the summertime. Colors of stars tell us their temperatures. Vega is one of three stars that are pretty prominent in the summer sky. It's called the Summer Triangle. It goes from Vega to Deneb to Altair and back to Vega. And if we backed up time just a little bit, all these other stars would disappear, and the first four stars you're going to see will be Arcturus, Vega, then Altair, and then Deneb. Altair is the 12th brightest star, and Deneb is the 20th brightest star. So of all the stars in the sky. So they're really the four brightest stars in the summertime. Soon after that, you'll see another bright one down low here, and that one will definitely have a yellowish orange color, and it might even have more of a reddish color. That's a star named Antares. And people often see Antares and they think it's Mars because it's so red. And it's interesting because it's right along the ecliptic, and the ecliptic is the path of the sun through the sky. And there's the path of the sun right there. And the planets follow the ecliptic. So about every 2 years, Mars comes by. And last year we had Mars and Antares side by side, the real Mars and the red star that's often mistaken for Mars. And interestingly, if you think about the name Antares, that basically means the false Mars, because it fools people. Ares was the Greek name for Mars. And ANT is like anti or all that root, so it means false or fake. So with kids, we talk about it being the fake Mars. Well, let's let it get a little bit darker. Shut the ecliptic off. And we're going to kind of concentrate on stars tonight. I always try to figure out a way to make these a little different from each other, because we've done so many of them now. The sky does keep changing through the seasons. You notice we're not looking at Leo the lion anymore like we did back in June, because Leo is up right now in the daytime. You know, if your astrological sign is Leo, your birthday is sometime in late July or early August, and you think that'd be a great time to see Leo. It's not, because the reason you're Leo is because during your birthday, the sun is actually in the constellation of Leo. Well, this red star, Antares, is a very old star, and it's near the end of its life. Let's just take a quick look at it here. And it's a red supergiant. So what does that mean? It means this is a really, really big star. Now let's compare it to something you're more familiar with, the sun. The sun, as you probably know, is bigger than the Earth. You could put 1,200,000 Earths inside the sun. So now compared to the Earth, the sun's pretty big, right? Now squeeze the sun down until it's the size of a beach ball, about 2 feet in diameter. Well, this star would be a 1/4 mile in diameter at that scale. It is a humongous star. It's a giant star, 1,600 feet in diameter compared to a 2-foot diameter sun. And that's a star that will die one day. When it dies, it'll explode in a supernova explosion. And I'm going to show you where that's already happened in the sky today, but we're getting ahead of ourselves. Now, when you find Antares low in the southern sky, that's part of the constellation of Scorpius, the Scorpion. And the Scorpion looks kind of like this. Let's take it off Antares and pick a different star. The Antares is the Scorpion's heart. His body comes down with a curly tail, and the bright star Shala is his stinger right here. These 2 stars mark his stinger. Come back up his tail to his heart. He's got a head in the middle and a claw here and a claw there. Well, when you find Scorpius, if you know anything about the zodiac, the next constellation over after Scorpius, or Scorpio if you're follow the horoscope, is Sagittarius, the archer. Well, these are the stars of Sagittarius right here. And Sagittarius, if you know your mythology, was supposed to be a centaur, which is half man, half horse. And as if that weren't bad enough or complicated enough, he's also shooting a bow and arrow. So look at this group of stars and see if you can see that. I can't, and most people can't. I don't know how you ever envisioned that, but it's actually a really easy constellation to learn if you turn into something it does look like, and that is a teapot. To see Sagittarius, the teapot, just draw the lines like this. Here's the base of the teapot, a side with a spout. Over here, a side with a handle, and up here is the opening with a lid on top. So it makes a nice little teapot. So if you can go out and find the Scorpion and you find the teapot, look between the spout and the Scorpion's tail, and you're going to see a neat little clump of stars right here. This is called Ptolemy's cluster. And Ptolemy's cluster is a group of very, very young stars. In this group, there are approximately, I don't know, 200 stars perhaps in Ptolemy's cluster. These stars are about 800 light years away. And from one side of the cluster, the other is about 50 light years across. These stars are really young. They're about 200 million years old. Sounds pretty old, doesn't it? For a star, that's kind of like being a middle school kid. It's like a 7th or 8th grader. They're just hanging out with their friends. So stars form in these open clusters, as they're called. And open clusters are scattered all over the sky. And they almost always have really young stars. Remember, stars can last for billions of years. So being 200 million years old is like being a teenager or a young teenager, as a matter of fact. And just like teenagers, they hang out with their friends, but as they get older, they spread out. Some go here and some go there, and some get married and so forth. And they spread out and they don't stay together as a group forever. And neither do stars. There's not enough gravity to hold these together. Over time, they're going to slowly disperse and disappear, and the cluster will go away. But they are all over the place. If you look just above it, there's another one. This cluster, by the way, is called Ptolemy's cluster because you can see it with just your eyes. Ptolemy, over 2,000 years ago, saw this little fuzzy patch in the sky. He wasn't sure what it was, but he wrote about it. And so it's been named after him because he was the first to make note of it in the sky. The one just above it looks smaller, and it actually is a little bit smaller, but it's also twice as far away. This is called the butterfly cluster because someone thought these 4 stars and these 4 stars look like the wings of a butterfly, perhaps. Well, you can use your imagination. What I always like when you get a cluster, though, is A lot of open clusters will have one or two stars that stand out by their color and have a separate color that's a little distance. And you can see there's a bright orange star in this cluster over here, and the rest of them kind of look whitish blue. So this is the butterfly cluster. It's another open cluster, just twice as far away. That's the main reason it looks a lot smaller than Ptolemy's cluster. So this is where stars, these are young stars, and these stars were born in this spot. To understand how they're born, let's go back over here to Sagittarius, the teapot. Put the lines back up for just a second. Go right up to the top of the teapot, right to the top of the lid. And if you have a pair of binoculars, scan off to the right, and right over here, you can see there's a little pink patch of light here. I'm going to shut those lines off because I don't really want to see them there. Come on. Oh, just hit the buttons, they'll all go away. There we go. And that little group of stars right there is a birthplace of stars. I did go away. There we go. It's called the Lagoon Nebula, and there's an open cluster right in the middle of it. So this huge patch of gas floating in space. This is a cloud of hydrogen. Stars are made of hydrogen. What stars do is they turn hydrogen into helium in their cores. So what happens is you have these giant clouds of hydrogen floating in space, and gravity has pulled them together. And as gravity keeps pulling the atoms together, it starts to make clumps. When the clumps have enough mass to create enough pressure in their cores to fuse the hydrogen to helium, that clump becomes a star. And there's enough hydrogen in this cloud to make maybe 200 or 300 stars the size of our sun. And these here are all young stars that formed from this great big nebula. Now, if you look at this with binoculars or with a telescope, you can see all this detail. You see these dark veins going through it. You see all these young stars. You see all the structure, but what you won't see is the red color. It really is red, but the part of our eyes that sees color needs a lot of light to work. And these things are very subtle. So when you look at it through a telescope, it's going to look grayscale, like you're looking at an old black and white TV set. These kids won't know what that is anymore, but they understand grayscale perhaps. So look black and white. And if you take a camera and take a picture, it'll very quickly show you the red color. I wish our eyes could see that. We can see it in the photography, but not in a live view. So this is called the Lagoon Nebula, and it's about 5,000 light years away. And from one end, this side here to this side, that's 110 light years across, 50 light years tall. So it's a really big cloud. Remember, a light year is not a length of time, it's a distance. It's the distance of a beam of light traveling at 186,000 miles per second. It's the distance that light will travel in a year's time. And so 1 light year is how far it goes in a year. So that means from here to here is 110 light years. So if you could travel at the speed of light and you wanted to go across the face of this thing, it would take you 110 years to cross it. It's really, really big. But that's where stars are forming. And if you could come back in 200 million years, this cloud wouldn't be there anymore. All these young stars would, but there'd be more of them. And what would be in their place would be an open cluster like we saw in Ptolemy's cluster. So this is where stars are formed, and they turn into open clusters like we saw below. And then the stars slowly drift away, and then they lead their lives. Stars like our sun, some stars are multiple stars. So let's come back out here and take a look at the stars and find a multiple star. Remember, I'm going to keep the glow off. We'll talk about that in just a moment. It's easy to learn the constellations if we keep the dim stars down for a little bit. Go up higher, and you'll see that summer triangle we talked about, Vega, Altair, and Deneb. Let's go to Vega. Now, Vega is the fifth brightest star in the night sky, and it's in the constellation of Lyra the Harp. And the way the harp is usually drawn is just as this little parallelogram. I often draw it as a triangle because most kids think of harps as big triangular instruments. So we draw a triangle like this. And you can draw it that way. Those stars are all part of the harp, but you'll often see it drawn as just this parallelogram, like a little harp like Nero might have played or something perhaps. Well, what I want you to look at, remember, stars have now drifted out from these, they formed open clusters, then they drifted out to form individual stars. Now, if a star drifts off by itself, it might be a star like our sun. If two stars drift out and they get too close to each other, the gravity pulls them into orbit and it becomes a binary star. And it's like two stars got married. But if a third star comes along and gets too close, it joins in and it's a triple star system. Well, this star right beside Vega, this one right here, is called the double double. So guess how many stars are in that? It's called the double double. Let's take a look. The pair of binoculars are pretty easily split into two. So that's a classic binary star. Now, if you have a telescope and you zoom in even further, let's zoom in on this one, you'd find it will split into two. Now, this program won't quite split it, unfortunately. That's a limit of the program I'm using. If you could zoom in just a little more, that would quickly split into two. So you won't split this into two without a telescope and probably 80x to 100x magnification. Then this will definitely split into two separate stars. And then if you go over to its companion over here, and with your telescope, look at that one, it splits into two stars too, but you notice they're perpendicular to the other. One's up here and one's down here. So that's 4 stars. And one of those stars, I think in this pair, is actually what we call a spectroscopic binary, which means one of those 2 stars has 2 spectrums, which means it's actually 2 stars. So the double double is actually 5 stars altogether, though you'll never split it into 5 with a telescope. With a telescope, you can see 4. With binoculars, you see 2. With your eyes alone, you only see 1. So stars in the middle of their life can be in the midst of complicated relationships, just like people often can. So we're getting into that aspect of it. So here we have kind of middle-aged stars doing their thing. Not all middle-aged stars are the same. This one here is Vega. This one's Vega. This one over here is Deneb. And Deneb is the tail of Cygnus the Swan. So this is the swan's tail. We go up to a star named Satyr, which is his shoulder. So that's the body between these two. I like to draw an oval, give him a little heft. A wing over here, and I draw a line back to the tail, fill that wing in. Another wing here, and I draw a line back to this tail. And then we have a long neck with a head right here. Now, Deneb looks like an average everyday star, but actually Deneb is a really powerful star. If you could see its color, it's blue-white, which tells us it's hotter. And it's incredibly bright. It's very, very far away, over 1,000 light years, I believe. And if you could put it side by side with the sun, it would be about 50,000 times brighter than the sun. So if we replaced the sun with Deneb, we really couldn't live on the Earth because the Earth would be fried by the power of this incredible star. So even those stars all form these nebulas, some form small, and some form big, and some are massive, and some are hotter, and some are cooler. It's all a function of how much hydrogen they have to work with. And the more massive they are, the shorter they live. They have a lot more fuel, but they burn it so ferociously, creating such a huge furnace that they live very short lives, maybe less than 1 billion years. Whereas medium-sized stars like our sun can last, maybe 10 billion years, not million, but billion. And small stars, which have the least amount of hydrogen, can last for billions and billions of years, much longer than the sun. So we find the colors tell us the temperatures and their masses, and it tells us a lot about how long they're going to live. So now we've kind of got stars formed. They formed into groups, teenage stars, so to speak. Now we got middle-aged stars. So let's go to old stars. Stars don't last forever. So right here, we've got the swan flying underneath. And right down here is a neat little constellation called Sagitta the Arrow. And it's simply that little line of stars right there. So you get the point of the arrow here and the tail here. And right above Sagitta the Arrow, we find a very famous dead star. So you come up above it, go from that bright star. I usually include this one, but you can if you want a longer arrow. Go right above it and look for this triangle of stars right here. And by the left star, or the eastern star, even with the head of the arrow, just underneath it, there's a fuzzy little patch. Maybe you can see it. Let's zoom in closer. And it definitely doesn't look star-like. You might see a little bit of a bluish color to it. And you might even pick up a little bit of that blue color with your telescope if you get a big enough one. The small one, it'll all look white again. You definitely won't see the red you're starting to see here now. This is called the Dumbbell Nebula. Now, the nebula we saw before, the Lagoon Nebula, is a hydrogen gas cloud that is collapsing on itself. It's collapsing into little clumps to become stars. So it's a stellar nursery. And we know that because if you take the spectrum of that, it's all just hydrogen. When you take the spectrum of a star, you get little black lines, they're called absorption lines, and different elements create very specific absorption lines. So you look at the Lagoon Nebula and we find it's all hydrogen. We look at this nebula and we find some hydrogen, you find some helium, and you find some neon, and you find some carbon, and you find some oxygen, and you find a whole bunch of other things. And that's because this was once a star like our sun. And when it got to the end of its life, it's turned all the hydrogen in its core into helium. Then it turned all the helium into carbon, and then it couldn't do it anymore. So it kept collapsing on itself. And finally, fusion started happening, not in the core, but outside the core, enough to push the outer layers away. And the outer layers get pushed away, not in a giant explosion, not a supernova, just pushed away, and they go drifting off into space. That's what this is. This is the shell of that those outer layers drifting away. And what remains of the core is deep in the center. It's what we call a white dwarf, not a black hole, but a white dwarf. It'll be about the size of the Earth, but incredibly dense. And it'll be white hot from friction. There's no fusion happening in there. And this thing's expanding outwards, this outer shell, at about 1,000 miles an hour, which sounds pretty fast, but for something this big, that's really not all that fast at all. This is 12,000 light years away, and this star died 48,000 years ago. So this is how much it's moved in 48,000 years. Now, there's another one I want to show you, and this one's younger, but it's twice as far away. So to find the next one, back to our friend Lyra the Harp. Remember, we saw the double right here, and there's Vega. Go down to the parallelogram and go between these two stars. This one's name is Sulafat, and this one is Sheliak. Go halfway between the two, right about in there. Let's center it so we can zoom in on it. And you'll find another one of these dead stars. It's actually right up here. This one's called the Ring Nebula. Look at this one. Now, this one is the same thing. It was a star similar to our sun. And this one died only 7,000 years ago, whereas the dumbbell was 48,000 years ago. This one's much more recent, but it's over twice as far away. So it's a lot smaller in the sky. It's small for two reasons. First, it's twice as far away, but it's younger, so it hasn't been able to expand as far as the dumbbell has expanded. But they're both what we call planetary nebulas. They have nothing to do with planets. They got that name because in the 18th century, after William Herschel discovered the planet Uranus, a real planet, he named it George, by the way, after King George. That didn't last very long, but that was his original name. Well, after that, people started looking for planets in the sky. Everyone wanted to be a discoverer of planets. And they kept finding these round things that were bigger than stars, but they didn't move like planets. And they seemed to have a nebulosity about them to some degree. So they became known as planetary nebulas. Maybe there are places where planets were forming in space. They weren't sure. We now know that they're dead stars, but they got it because of their resemblance of planets and being disks in the sky. And the Ring Nebula and the dumbbell are two very good examples. You can see how small that is. You can still see it right there if you look carefully. So that's how stars the size of our sun will die. Our sun will never explode. Only giant stars explode. So let me show you where one has exploded. Come back to our swan. So we're kind of bouncing back and forth between these constellations here. And come down this lower wing right here, and right off the tip of the wing, right about in this part of the sky, with a telescope, or even better with a camera. This is one of those things that's hard to see in the telescope. I've seen it a couple times, and it's big enough in the sky you can't see the whole thing in the like we can here in the telescope, because telescopes look at a small area like this. So you might see the better part of that or the better part of this, but you won't see the whole thing. If you take a photograph of this whole area, it'll show up, but its surface brightness is so faint that you won't even see a gray cloud for the most part. But you can see it here. You see that This is called the Veil Nebula, and it's very wispy-like. And this was a supernova that exploded. And when the Veil exploded 15,000 years ago, in our sky, if you'd been around back then and looked up and saw this when it exploded, it would have been as bright as the full moon. And yet it would have been, when it exploded, it was a single star. It would have been a single point of light. It would not nearly have been as big as this. But imagine a single point of light as bright as the full moon. It would have hurt your eyes to look at it because it was so intense, because it was so small. And when that star exploded, it created everything heavier than iron. Now, stars can create everything up to iron. Once you get to iron, no matter how heavy the star is, it cannot fuse iron into anything else. It takes a tremendous explosion to make things heavier than iron or denser than iron, things like silver and gold and platinum and uranium and plutonium and anything denser than iron on the periodic table. So supernovas, what create those things? So given that, think about this for a second. If you have a wedding band on your finger right now made of gold or silver, or you have silver earrings or golden earrings, every ounce of silver and gold on the planet Earth was created in one of these explosions. If you have a piece of jewelry on your body now made of silver or gold, you have a piece of a supernova on your person right now. Isn't that cool to think about? So when Carl Sagan said, "We are star stuff," he wasn't being metaphorical. Everything on the Earth was created in a supernova. This is second generation material. It was created either in the core of a star or in a supernova. And we know things heavier than iron were created in supernovas. If you touch your nose with your finger, our noses are made of carbon mostly, some water and stuff, but mostly what you're feeling is carbon. Carbon's created in the core of a star. So when you touch your nose, what you're touching was once in the core of a star. Kind of cool. So that's a star that has exploded. And luckily, they don't explode nearby very often because they're pretty traumatic things. When they do explode, though, and we have a couple stars that might sometime, like Antares that we talked about earlier, the heart of the scorpion down here, or in the wintertime, the star Betelgeuse, which everyone's heard of, which is an Orion shoulder, which is another red supergiant. They're due to explode sometime within the next million years. It may be tomorrow, or it might be a million years from now. And when they explode, they're not close enough to hurt us, but they will certainly light up the sky, and it'll be a tremendous show for those who are around to see it. So we've kind of gone through the life cycle of a star. We found a place where stars are being born with the Lagoon Nebula down here near Sagittarius, the teapot. We found young stars with Ptolemy's cluster, the butterfly clusters, hanging out with their friends. And then we found some interesting double stars like the double-double. Another very famous double is this one right here, the head of Cygnus the Swan, star named Albireo. With your eyes, it looks like a mediumly bright star, nothing special. But with the telescope, it quickly splits into two. And this is one that's prettier in the telescope than it looks here, because they're two different colors. One is blue and one is orange or gold. Different people see it slightly differently, but everyone sees two different colors, either gold or orange, and the other one's blue or almost indigo or violet, perhaps. That's because of the different temperatures. And the colors are much more intense here when you look through a telescope. Stars are pinpoint spots, and so if they're bright enough, that can affect the cones in your eyes so you can see that. So that's one color shows better than it does in the program, unlike the nebulas, which is the other way around. So that's Albireo. And I'd like to show you one more that I just saw. I went to a star party this past weekend at Cobscook Bay State Park. It's called the Main State Star Party. And there were probably 20 or 30 telescopes there. I had mine. But a friend of mine, Larry, said, "Hey, let's look at Piazzi's flying star." And that's in Cygnus the Swan. So we see Cygnus right here. And there's Deneb, which we talked about. Come over here on this wing, and you're going to notice a nice little triangle here. Two bright stars and a fainter one. We're going to look at that fainter one because that is Piazzi's flying star. And it turns out to be a binary, two golden binary stars. And with just a small telescope, you can easily split those two, and they have a nice golden color, which means they're a little cooler than the sun, hotter than Antares or Betelgeuse, though. But that's not why they're famous. This pair, there are lots of binary stars in the sky, but these two move. Over time, if you look at pictures of them taken about 100 years ago, they were back here. These stars were all in the same spots, but these two were sitting about over here. They actually move 5 arc seconds across the sky every single year. So that's why they're the flying star, because they're moving together through the other stars. And what that told astronomers 200 years ago is that these two stars have to be a lot closer than the background stars for us to see their actual motion. Because the other ones are moving too, but they're so we can't really notice their motion. So this is one of the first star pairings or first stars that we actually could see its motion through the sky. And using that, setting it against the background stars, they could see parallax. Now, parallax is like if you've ever taken your thumb and you hold it up and you blink your eye back and forth, and your thumb looks like it's jumping back and forth against whatever you're in the background. Well, stars will do that too. If you look at these two stars through a telescope, you can see fainter stars behind it. In this program, we can't do that. But with a telescope, you could, and you'd see that from one side of our orbit, let's say in August, you look at them. Then you look at it again when in January or February, and you'd see that they shift against the background stars. Back to August, they shift back again because we're moving from one side of our orbit to the other. And using some geometry, they're able to calculate the distance to the star. And they calculated it at 10.4 light years. We now know, because our tools are better, that it's 11.4 light years. But this was the first star other than the sun they were actually able to calculate the distance and be somewhat accurate about. So that is Piazzi's flying star, and it's in Cygnus the Swan. So just looking at some individual stars, we find some interesting things. Now, if we were on Quill Hill right now, which is where I wanted to be with all of you folks this evening, the sky wouldn't exactly look like this, because this is the way the sky might look for me here in the greater Waterville area, not in the city, but out in the countryside somewhere. But in Quill Hill, or most any place around the Rangeley Lakes, you get a much darker sky, and the sky is going to look a little bit more like this. You're going to see a lot more stars, and you might notice that that Milky Way just popped into view. You could kind of see it before, but not like you can see it now. That's a function of being in a dark spot with less light pollution. You know, here in Waterville, if I get out in the countryside and I'm maybe 5 or 10 miles from Waterville and 20 miles from Augusta and 25 or 30 miles from Farmington, then you get some light from those towns and cities, and they wash the sky out, and the sky will look more like this. For teaching using this program, it's easier to see the constellations this way. For outside, though, in a nice dark spot like the Rangeley Lakes, you're going to get a much denser sky field. And those constellations will still show up fairly well outside, though it gets a little more challenging here. You know, if you look, you can still see the swan right here. We can put some lines on it. Let's do it right. There's a swan, and there's the harp, Lyra the harp. Down here, we can see Scorpius the scorpion. And right here is Sagittarius. And to make that teapot, we're going to get a whole bunch of other things here. But you can see there's the teapot. The teapot's what's called an asterism. It's not actually what the constellation is supposed to be. It's just what it looks like. All those other ones are the asterisms around the sky. Some I pay attention to and some I don't. The teapot, almost everyone does. But it's made basically of Sagittarius. Now, the way they draw Sagittarius, the official way is like that. And to me, that doesn't look really anything like a centaur either. So I don't know how you quite get that from there. But anyway, let's shut them all off. And I want to talk about that Milky Way. So Milky Way is our galaxy. We live in this giant galaxy of about 300 billion stars. The sun is one of those stars. So when you look up and you see this band of light, you should realize, kids say, how far away is the Milky Way? That's a question I get a lot. We can say, how far away is, Antares? Well, that's 800 light years away. And we talk about the distance to some of these clusters. Ptolemy's cluster is 800 light years away. The Butterfly cluster is 1600 light years away. The Lagoon Nebula is 5,000 light years away. Well, the Milky Way, you're in it. So it's not any miles away. You can go to different parts of it that are thousands of light years away, because the Milky Way is 100,000 light years across. but you don't get any closer to it because you're inside of it. You just move to a different part of it. So it's shaped like a Frisbee made of stars. And we look at this band, we're looking into the thickness of it. All these stars up here and all these stars down here, they're part of the Milky Way too. It's like looking out the top, looking out the bottom when you're inside this Frisbee made of stars. Follow that Milky Way across the sky, past Cygnus the Swan. There's Cygnus. Oh, let's put Cygnus up there. There's our constellations we've been talking about. Keep going across the Milky Way. The Milky Way starts getting a little fainter in the northeast. You'll find the famous W of Cassiopeia, the Queen. And Cassiopeia, if you want to find more open clusters, there's tons of them all around here. Take out your binoculars and just start scanning. Let's just take a quick look in here. Well, let's zoom in and get it centered here. And looking around, you see there's a cluster right there. There's another cluster over here. There's a really nice couple clusters up above here. Look at this one over here. See that cluster right there? So there's tons of clusters in here to explore, some interesting double stars as well. But there's one cluster here I'd really like to show you. It's called the double star cluster. It's right down in here. You can see it with just your eyes, but with a telescope, the best way to see it's not even with a telescope, it's with a pair of binoculars. It's right here. You get two open clusters, one here and one here. It's known as the double star cluster or the double cluster in Perseus. And it's like two little piles of diamonds. And these are all young stars, maybe between 100 and 200 million years old. So if you've been around 200, 250 million years ago and you looked at this spot in the sky, you would have probably seen a very big and complicated nebula, like the Lagoon Nebula. That nebula is long gone. It's all formed into all these stars. And it's a really easy thing to see with the pair of binoculars. You can see with your eyes, it looks like two fuzzy little clumps, kind of like Ptolemy saw when he looked at Ptolemy's cluster. These you can see a little easier for us because they're higher in the sky. Now, as I zoom around here, you notice there's nebulosities here, these red spots are places where stars are forming. They're not even going to show up in your telescope. They're there. If you take a photograph, they show up, but with your eyes alone, they're just not going to show up. So I can shut them off because you won't see them with your eyes and you're not going to see them with your binoculars, but you will see these clusters of stars. Now, the Milky Way is our galaxy, but our nearest neighbor is not too far away, and it's right underneath Cassiopeia. So you find Cassiopeia, the Queen, and look underneath it, and kind of down into the east from Cassiopeia, you can see a great big square tipped up on its side. That's called the Great Square of Pegasus. Pegasus, as you may know, was the flying horse. And to see the flying horse, it looks like this. Doesn't that look like a horse? Well, the horse is supposedly flying upside down. You can do that in space. And this is the back of the horse. This is the chest of the horse. Here's the horse's neck. So the mane would hang up here if you drew a neck on it. This is his head with his nose out here. And these are front legs right here. You can put a drawing on this. You can visualize it perhaps a little better like that if you want. They don't actually draw the wings on with any stars. You just use your imagination for that if you like. The fourth star in the Great Square is shared with the constellation of Andromeda the Princess, and it's Andromeda's head. Now, I don't like the way this program draws Andromeda, so I'm going to show it to you the way I like to see her. So think of Alpheratz, that's the name of the star, as her head. This triangle right here is her body. The belt is right here, and so she has this triangular body coming up to her head. She has an arm here, and then an arm over here with those three stars. Come down to the belt around her waist, and she has a leg down to Almach, and a leg over to this star. I don't know the name of that one. And if you look carefully, there's a nice little line of stars between her legs. That's the hem of her dress right there. And she's kind of floating sideways. Now, they don't draw her that way. They just draw a line down one side, whereas I draw a line down the other side and all the way down to this star and give her two legs. And then I give her some arms too. Either way, what the key thing here is find Alpheratz, go down to Merak. This one's Almach, and this is Merak. Then go up two stars her belt, and just beyond that, you'll see a fuzzy little star right there. You can just barely see it with your eyes. Zoom in just a little bit. You'll show it a little better. Looks like a star that's that someone tried to erase, perhaps with a bad eraser, and they just smudged it out. Now, if you're having a hard time seeing it, if you're outside and you look at it, it'll seem to disappear because it's faint. That's a trick of your eyes. You pick any faint star and stare at it outdoors, it'll seem like it disappears. Look off the side and it reappears. That's a function of your eyes. In the center of your eyes are the cones, which see color, but they need a lot of light to work. So if you stare at something faint, all the light's hitting the cones, and the cones don't register as anything hitting it, so it just disappears. Around the edge of the cones are the rods, and rods can't see color. They see black and white, but they can see very faint light. So when you look off the side, the light comes in your eye at an angle, and rather than hitting the cones, it hits the rods around the edges and it reappears because the rods can see it just fine. So to see that, when you go outdoors and you want to see that little smudge of light and you can't quite see it, don't stare at it. Stare at this star. Now, at the corner of your eye, you'll see a little smudge just above that one. Now, if you have some binoculars and you look at it, it's going to look like definitely a smudge of light. You can definitely see this smudge right here. And it'll be kind of oval shaped. But that's about all you'll see with a pair of binoculars, and maybe a 4-inch telescope won't show you much else. If you have a bigger telescope, like the one I'd be bringing to Quill Hill, then you'll see a little more detail. And if you take a photograph, then it's going to look like this. Now, it won't quite look like that through my C8. You'll see something kind of in between the two with my 8-inch telescope. With a larger telescope, you'll start to see some of this structure here. And if I took a photograph of it through my telescope, you would see all this structure too. Though I've never actually seen any blue light, see the blue around there. That shows up in some photographs if you sensitize it towards certain elements and things, but you can definitely see all this structure if you take a photograph. Cameras can gather light over time and build an image, and your eyes can't quite do that. So photography often has its pluses to help you see things you can't see otherwise. So that's the Andromeda Galaxy. It's very, very similar in size to our Milky Way, maybe slightly bigger, have maybe 350 or 400 billion stars in it. And it's the closest spiral galaxy to our own. We're looking at it, it's at about a 45-degree angle. So we're not looking flat down from the top, we're looking at it at an angle. And it's 2,500,000 light years away. So that means when you look at that through a pair of binoculars like this, or through a bigger telescope and you see something like that, that what you should realize, the light that's hitting you in the eye at that moment took 2,500,000 years to get to your eye that long. So what you're seeing is with the way it looked over 2 million years ago. It's not how it really looks today. And the light that's leaving it right now will not reach the Earth for another 2,500,000 years. So when you look out in space, things that are really far away, like galaxies, you're looking back in time. And the farther away they are, the farther back in time you're looking. So studying space is really is sort of a time machine when you're especially looking at galaxies and things like that. And that's a special one because it's nice and bright, and it's really, really easy to find in the sky. You can see it with just your eyes. And if you go outside, you don't have binoculars or anything, but you're in a nice dark spot, like you might have if you're somewhere in the Rangeley area, and you can locate that little fuzzy point of light, you should realize that with your eyes alone, that's the most distant object you can see. Now, with a telescope, you can see things much further away, but with your eyes, you won't see anything, eyes alone, nothing further away than that object. And that's kind of interesting to contemplate, I think. So what I'd like to do now, we've been looking at the sky just after dark, maybe around 9:30 here. And I want to keep you up a little bit later, not too much later, but just a little tiny bit. So you can see, and where I want you to be looking, maybe around 10 o'clock tonight, or tomorrow night if you get outside, or the next night, anytime soon, you're going to see something bright coming up. So let's go ahead in time again, just a little bit. We'll speed up time and look over in the east southeast, and there it is. See that bright object that just came up right there? It has a slightly yellowish color. That's worth staying up for. That's not a star at all. That's a real planet, and that's the planet Saturn. So between 9:30 and 10, you're going to see Saturn, and how early it is depends on how many trees you have in the way. If you got a nice view looking off to the east, southeast, out across the lake, so you got a really distant horizon, it's going to rise a little earlier. If you got trees to the south, southeast, you got to wait till it gets above the trees. So it can vary. Now with your eyes, it's just going to look like a mediumly bright yellowish star. And it does have a distinctly yellowish color. And if you have a telescope, you definitely want to check it out. With a telescope, you'll see rings of Saturn. It'll probably look about like that. Now, you've all seen pictures where it's much, much bigger, a lot more detail. And those pictures that you're used to seeing were taken by the Voyager space probes or the Cassini space probes. Those are machines we actually sent to Saturn. Voyager 1 and Voyager 2 flew by Saturn and sent back all these incredible pictures that we all grew up with. And then the Cassini, 10 years ago, went to Saturn and went into orbit and stayed in orbit for 7 or 8 years, sent back thousands and thousands of pictures of Saturn. Through a telescope, it's not going to quite look like that. It's going to look small, like this, and you'll definitely see the rings. They're going to stand out clearly to you. But people often looking at it, wow, it looks so small, but I can see so much detail on it. Well, you're still, remember, this planet is 1 billion miles away, not 1 million, but 1 billion. And 1 billion is 1,000 millions stacked on top of each other. So it's a long, long way to Saturn. Saturn is 700 times bigger in volume than the Earth. So it's a fairly big planet. Let's get rid of those blinking lights. And it's not like the Earth. There's no ground. We can't send rovers there the way we've sent rovers to Mars because there's no ground to land on. It's clouds and gases and liquids deep inside. And the winds on Saturn blow around 700 miles an hour. It'd be a wild ride to fly into the clouds of Saturn. So people often wonder, if you can't land on the planet, could you land on the rings? Let's stop the motion there. There we go. Well, even though we won't be able to zoom in with our telescope much more than this, with this program, I can zoom right in close. So let's take a closer look, a little bit better than you'd see with a telescope here. These rings from the inside edge here to the outside edge there, that distance is like 30,000 miles. That's a long way. 30,000 miles across. And the rings are made of ice, mostly water ice. So if you took a chunk of Saturn's rings and melted it, you could theoretically drink it. Now, there might be some other things mixed in with that water ice that maybe you wouldn't want to drink, but it's primarily water, frozen to about 300 degrees below zero. So it's frozen, so it's as hard as a chunk of granite. It's not a sheet of water. It's not like a frozen lake. These particles, much more like crushed ice you'd put in a soft drink in the summertime without the soft drink, just little chunks of ice. Some might be as big as a house, but most of them are the size of chunks like you'd put in a drink, little ice cubes. And there are billions of them in an asteroid field going around Saturn. 30,000 miles wide, but if you measure the thickness from top to bottom, there are places it gets to be as much as 1 mile thick, but those are the rare places. Most places it's less than 100 yards thick. Less than 100 yards. Think about that. You're looking at something 1 billion miles away that's less than 100 yards thick, but 30,000 miles wide. That's amazing. All these dots you see around here are moons, and their size is greatly exaggerated. They're much, much smaller. The big one here is Titan, and Titan is Saturn's largest moon. It's the largest moon in the solar system, way bigger than our moon. It's actually bigger than the planet Mercury. So people often say, well, why isn't it listed as a planet? Well, planets orbit the sun and moons orbit planets. Titan orbits Saturn. So even though it's bigger than one of the planets, it's still a moon because of what it's orbiting. It's orbiting a planet. Titan also has an atmosphere of methane. And if you landed on methane, we've landed a space probe there, not with people on board, obviously, but it landed. What we found is on methane, where it's pushing 250 to 300 degrees below zero, methane works at those temperatures the way water does in the Earth. There are actual lakes of methane on the surface, clouds of methane, and it rains methane, it fills the lakes. There are methane rivers. Works very much like water on the Earth, only at much colder temperatures. Interesting place to learn more about. So that's the planet Saturn. You want to check it out. And you'll see Saturn, you'll probably see Titan. It'll look like just a dot. It won't look nearly as big as this. It's not nearly as big as Saturn. It's just the way this program works to emphasize the moons. And the other moons, you'll be lucky to see it all unless you have a really, really good night and a really good telescope. So that's Saturn. You want to stay up till 9:30 at least to see Saturn. But if you're really into it and you're really enjoying the sky and you find yourself staying up a little bit later, let's say to maybe 11 o'clock or so, let's just stay up late. Why not? You're going to find another planet rising. There it comes, and it's even brighter than Saturn. And that is the planet Jupiter. It rises between 11 and 11:30 right now. By September, it'll be rising right by 9 o'clock. So right now it's rising kind of late, but it does come up and you can check it out, and it's worth visiting too. If we look at that with a telescope, you're going to see Jupiter and you're going to see its 4 large moons. Now, again, this program makes the moons appear larger than they really are. They're going to look like dots, like stars, but they're going to be, there's 4 of them, 4 big moons. It actually has over 100 moons going around it, but most of them are very tiny. And with a backyard scope, you'll only see the 4 big ones. And you see Io, and I'm not sure which one's a which here. That one's Ganymede, Callisto, and over here, that's a star. I guess the other one might be behind the planet. I knew that one was Io. I thought that might be the 4th one. You don't, oh, that's a star in the distance. Sometimes you don't see all 4 because occasionally a planet, one of the moons will be directly behind the planet. I've been out before where you see 3, and the 4th one was actually behind one of the other moons. And I had a student looking and explaining how it might be behind Jupiter, and suddenly he said that moon just turned into 2, and they seem to separate apart. So we get to see that happen. That was kind of cool. If you look at Jupiter itself, you'll see these bands going across it. Jupiter's like Saturn. It has no ground. You can't land here. It's all clouds and gases. And the wind blows through the clouds. And in one band, the wind will blow east. And the next band, it'll blow west and then east and then west. And so it creates these opposing winds swirling around the planet at over 100 miles an hour in different directions. And that creates storms like the famous red spot. And we have this set for tonight. And at this point, the red spot's not facing us, so we can't see it. It's challenging to see the red spot. I've only seen it a couple times. You've got to have the good conditions and nice clear sky to see it in a good telescope. The cloud bands, you can usually see 2 gray cloud bands pretty clearly when you look at Jupiter. Jupiter, remember, is the largest planet. It's 1,000 times bigger than the Earth. And as big as that may seem, compared to the sun, it would take 1,000 Jupiters to create the sun. So it's a wonderful thing to look at. My 2 favorite planets to see in the sky are the 2 that we're seeing this evening, Jupiter and Saturn, because they have the most detail of what you can look at when you look in the sky. And if you stayed up late enough to see Jupiter, then you'll notice just to the left, another open cluster. We've talked about them, like Ptolemy's cluster or the butterfly cluster or the double star cluster. This is the most famous cluster. It's one we associate with winter. And in August, if you stay up all night, you'll find that before the sun comes up in the morning, Orion the Hunter, a famous wintertime constellation, will arise. Well, we're only here now at around a little after 11 o'clock, and we find the Pleiades, which aren't that far from Orion. And the Pleiades star cluster is best seen with binoculars. It's big enough that when you look through a telescope, you can't see the whole thing. Telescopes will just look at a little part of it. With binoculars, you can see the whole thing, and it'll look like this. Little pile of diamonds in the sky. And these stars are about 70 to 100 million years old. And you may see a little bit of nebulosity around them. You know, this is what it looks like with your eyes. Take a photograph, it'll look like this, and you'll see a lot of nebulosity around them. And for a while, it was thought that that was the nebula they form from. But they have done measurements and found that that nebulosity is actually floating between us and the cluster, and it has nothing to do with the cluster. It's just nebulosity floating in space between us and the cluster of stars, and the starlight shining through them and lighting them up. What you find is sometimes you see these nebulas, and you'll see a nebula without the cluster, but it'll look blue. And the difference between a blue nebula and a red nebula, they're both made of hydrogen. They're the same thing. The difference is when they're red, it's because there's a lot of young stars mixed in with the cloud, and young stars give off lots of ultraviolet light, and that excites the molecules of hydrogen enough that the hydrogen molecules actually start to glow. And when they glow, they give off red light. Now, if the stars aren't close enough to excite the molecules to make them glow, but there are stars close enough by to light it up, the way you shine a flashlight on something and light it up, then the hydrogen glow will be lit up and it'll appear a bluish white color. And that's what we're seeing here, is that bluish white color. These stars aren't close enough to make it glow. If that nebulosity were actually amongst all those stars, it'd probably be glowing with a more of a red light. And that's not what we find with the Seven Sisters. So we found some interesting things here tonight and kind of looked at the life cycle of stars a little bit. seeing young stars and baby stars, where stars are being born, like in the Lagoon Nebula, teenage stars like the Ptolemy and the Cluster and the Pleiades or the Seven Sisters here. We found some dead stars, the Ring Nebula and the Dumbbell Nebula, then an exploded star with the Veil Nebula. So we're kind of went through the whole life cycle, and we found some interesting binary stars too. So I hope you've enjoyed our tour here this evening. I'll try to make it a little different than what we've done each time, just to keep it fresh.